All right. Good morning, everyone. So today we're gonna continue our preparation. So we are still discussing. We start for a new topic, a new chapter. So the previous one we already discussed about uh aqueous and solution reaction, which is talking about kind of like molar concentration, and then many things that we discuss. Okay, you can take a look at my previous video before this video. So we done for the chapter 9. So today we gonna discuss for about kinetic energy or kinetics, right? Not energy, kinetics, kinetic reaction. So just quick heads up that this chapter will cover uh some subtopics such as rate, like determining a rate law, okay, initial rates, and then half-life problems, and then collision theory, and then activation energy, and then mechanism, okay, reaction mechanism, and then relationship between kinetic to and equilibrium. Okay, so let's get started for the first question. Now we start from study question first. Okay, study question first. Okay, if you want to take a look at your textbook, okay, if you want to take a look at your textbook, you can refer your textbook in normally the chapter's name is like kinetic, chemical kinetic, or just kinetics in your textbook. Okay, so it's pretty easy. Just take a look at in your textbook about kinetics. Okay, sounds good. So now we start from the first chapter. Okay, just I need to clarify that what taught here, what I explain here is ACS exam preparation. Okay, ACS exam preparation. So what I post over here is regarding this exam. Okay, regarding this exam. And then the thing that make it beautiful, because I always explain the theory or key concept of each question. All right, so now let's get started. So the first question is, oops, sorry. What is the rate law? The rate law of this. Okay, what is the rate law of this? Why? Okay, and then, yeah. Okay, what is the rate law of this reaction? Okay, what is the rate law of this reaction? Okay, now first of all, we need to know what's the concept of it. Okay, understand the key concept. Okay, the rate law express how the rate reaction depends on concentration of the reactant. Okay, again, the rate law, okay, is like expression how the rate of reaction depends on the concentration of reactant. So we determine the order of the reaction with respect to each reactant by saying how change in concentration affect the rate. Okay? Now let's start from the trial 1 and trial 2. Okay? So Okay, so now let's move on. Let's start to compare trials for each experiment. Okay, now in the first experiment, the rate. Okay, the rate is from here. The rate is Kn2. Okay, which is K is constant, right? And then there is M over here, and then there is also hmm, okay, so you are given the initial concentration and initial rate from three trial. The rates law. Okay, so N2 and then NO. Sorry. So not this one, sorry. So the rate is K, the general form, the general equation is K H2 and then M times NO, and then this one is N. Okay, this is the rate. Now compare the trial 1 and trial 2. Trial and trial 3. So trial 1 and trial T. And O in trial 1 and trial 3 is constant. Okay, constant. And then for H2 is double. Okay, H2 in the trial 1. Okay, and then double in trial 2. Trial 3, sorry, trial 3. Okay, trial 1, trial 3. Okay, so rates rate goes rate goes from 2 to 4. So again, this one is also the double. Okay, so the rate is, okay, the rate 3 divided by rate 1 is H2. What is it? Okay, rate 1 and rate 2, it should be 4 divided by 2, and then this one is 2, right? Okay, based on this one, 4 divided by 2. And then how about the H2? The H2 for reaction 3, okay? I mean for the trial 3, H2 from trial 1, 2 per 1. So this one also 2. That means 2m equal 2. So m it should be only 1. Okay? M should be only 1. So rate it should be what? K H2 1. Okay, H2 1. All right. Okay, so we continue our discussion. So H2 is 1, right? And then we need to know for the NO. Fortunately, the other option, okay, there is no H2 with the 1. Fortunately, there is no option for H2 power 1 except option B. However, if we look, if I mean the if the option has some, okay, if the option has some, so M should be, wait, so wait. Just wondering, like rate 3 divided by rate 1, 4. So 2, so M, it should be 1, right? It should be 1 because this one is 2, and then this one, and then N should be 1. M, okay, sorry. M, it should be 1. How about for NO? For NO, looking at we can compare rate 2 and rate 3 because this one is constant, right? This one is constant. So rate 3, rate 2 is from rate 3 is 4, then 3, and then 1.6, then 4. So it should be 16.3. So we can cancel out this one. For 16, it should be 1. Mm. So 4 divided by 16, so it should be 0.25. And then how about the NO? 3 NO 2 is 2 divided by 1, 1 divided by 2, and the result is 0.5. Okay, 0.5. And yeah, okay, so 0.5 square, I mean N, and then the output is, the rate is 0.225. N is what? 0.5 times 0.5, so 0.25, so it should be 2. So M should be 1, and then N should be 2. So K, H, 2, 1, and O, 2. This one. Okay, just remember the concept of rate law. Okay, rate law. So rate law is the expression. Okay, rate law is the expression how the rate reaction depends on the concentration of the reactants. Okay, And then we can determine the order of the reaction by saying how change in concentration affect the reactant, the rate, sorry. Okay, so we got the answer. The answer should be P, right? Should be P. Okay, and then what's the why the option A doesn't this one is incorrect. The rate A is wrong order. The option C is H2 should be first order, not the second. The rate 3, you see over here. Okay, over here, product never appear. Okay, never appear. Remember, in the rate law, okay, in the kinetic rate law, uh, rate law for the product shouldn't be appeared. Okay, shouldn't be appear. All right. Now let's move on for another equation, for another problems. The rate law of the reaction blah blah blah. If A is first order in A and second order in B, so the rate is K. This is first order, and then the P is second order. Okay, if A is half and B is double, if A is half and B is double, like for example 1, okay, so if double is if okay, for example, if the previous one is 2 and then 2 square, right, something like that, and then if we convert it with this one, if half, so K will be 1, right, and then double, which mean 4, and then like this one, right, the rate of reaction will be increased by what? So 2 2 2 2. This is 8, this is 16. So increase by factor of 2. Okay, increase by factor of 2. Probably the answer. Okay, increasing by factor of 2. Okay, that's correct. Okay, so the half-life for the first order conversion of cyclobutene to ethylene is blah 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 at particle temperature. How many seconds are needed for partial pressure of cyclobutene to decrease from 100 to 10 mmHg? Okay, it's quite complicated for this one because it's involved kind of like some equation. However, if we know this is the concept of half-life. Okay, half-life. The half-life is 2.7. Okay, so let's break it down first. Okay, the first order, there is a clue over here. First order. Okay, the half is constant. Half is constant. Okay, and independent. Independent, right? Independent. So the equation will be what? T 0.693 divided by K, or we can use ln A 0 A K T. Okay, we can use such as this one. So now this is the for the first order. Okay, for the first order. Okay, so now I just wanted to revise this one. So I don't want to like give you equation directly. However, I want to you to think like how it's coming from. Okay, how this come, and then one by one. Okay, okay. So the half-life for the first order blah 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 is 22.7 at particular temperature. So you are asked that the half-life of this reaction is 22.7. That means every 22.7 second, okay, half cyclobutane disappear. Okay, now the question is how long will it take? How long will it take for the pressure to drop from 100? How long? 100 mmHg to 10 mmHg, right? So now let's understand first what's the meaning of the first order. Okay, the first order is like how much of it is left. Okay, so the speed which substance disappear, only how much of it's left. Okay, if you start from 100, after like one half life, which is uh 22.7 second, it becomes like only 50 millimeter Hg. Okay, after two half life, okay, so after one half life, okay, which is 2.7 second, and then after two half life 45.4, okay, it becomes 25, and so on until after four half life it becomes like 6.25 millimeter Hg. Okay, but our question doesn't land exactly on one dose of nice half-life point. So the question is how much has the pressure dropped from the 100 to 10, okay? So how many times do you have to cut from 100 to get 10, okay? To get 10. So let's figure it out. Like from 100, okay? From 100 becoming 50, right? So we have like for example, from if you don't remember the equation stuff, okay, for example, so every fifth, if we have like 50, uh so start from 100, right? If we use 22 second, right, we we only has the remaining of the cyclobutane like 50 mmHg. If we use like uh this is one half life, right, and then two half life of this one, for example we adding more, so it will be 45.4, so it becomes 25 millimeter Hg. And then if we use again like the 3 half-life again, which is we adding this one, so it will be what? It will be 1, and then this one is 8, and then 6 8.1, and then it becomes what? 12.5 millimeter Hg. So now we need to figure it out. Okay, we need to figure it out. So and then a 4, just adding this one, and then 90.8 second, and then it will be 6.25 millimeter Hg. Now let's figure it out. Okay, from this part, we know that it will be between this second and then another second. Okay, so between third or fourth half-life. Okay, so we need something more exact right now. Okay, so the idea is how fast the reaction goes. Okay, because this one is first order, we can use the standard idea. Okay, how much you had. Okay, how much you had divided by how much left. Okay, and then how many times. Okay, so in math formula, we know that ln, okay, initial pressure divided by final pressure, and then we know K and T because this is the left one, the times that we need to know. So actually, based on this option, guys, based on this option, we know the answer will be C. Okay, directly without any kind of calculation. Why? Because we know from this option, from the first order option. Okay, so if you don't want to use the equation, we just, I mean, in the option is only this one is beyond to fourth half-life, this one less than the third half-life, which is we have more than 12.5, right? And then this part is 75, so in between 68 and then 90.83. So so now instead using this kind of method, we want to know the exact number. We can do it. Okay, we can do it. How to do it? So we know the from the first order. Okay, from the first order chemistry, we know that half-life is 6 point this one, right, divided by K. Okay, so K, it will be 0.963 divided by what it is, divided by 2.7 to 2.7. So the K will be 0.0305 second minus 1. Okay, now we can plug in into here. The initial pressure is 100, the final pressure is 10, the K is 0.0305, and then we know T. Okay, now based on this one, we can get the T is 75.5 second. So final answer is C. Okay, so if we don't remember, okay, if we don't remember this equation, right, just use this concept. However, this one can like shorten your time to solve this problem. Okay, right. Again, the half-life for the first order radioactive of 32P is 14.2 days. Okay, how many days will be required for sample containing this one to decrease to 20% of initial activity? Okay, so we can use the previous concept. Okay, let's start from, let's we want to solve this problem without any equation. We just wanted to know just by using the logic thinking. Okay, logical thinking. Okay, now we know the first order. Okay, so the half life. Okay, 50% of the sample need uh will disappear within 14 to days. Okay, with the first half. Okay, from 100%. Now we need to use the again the two half time, which is 25%, and then we just adding for this one becoming 28.4 days. Okay, now we need to again knowing this part again, so half for this 12.5 per percent, and then it needs like 6, 12, and then 42.6 days. So now we have to get the answer. So we need to determine the days just in between 28 and then 42. Which one the in the option that in this range? You just A. We can get the answer directly. Okay? Without any put in any kind of equation. We can solve the problem easily. Okay? We can solve the problem easily. Because of what? Because we know the concept behind it. Right? However, if we want to use the exact amount, I mean exact days, the problem is if we have option kind of like 33 or 35, we don't know which one that correct. So we need to use the option half time. Okay, so over here we can use T 0.693 divided by K. Okay, so this is the half. So this one is 14.2, 0.933. So K will be 0.0488 days. Right? Now, we want to use ln. The initial one is 100. The final is 20. And then K is 0.0488 times days. Okay, over here. So let's take a look at the answer. Ln 5 is 1.609. Okay. This is T. So just divide it by 0.0488. So the answer will be 32.98. So the answer is same. Okay? The answer is same, A, right? Okay, just remember the concept. Okay, now let's move on to another question. Plots are shown for the reaction NO2 and half O2. What is the rate law for the reaction? Okay, now as you can see guys, the reactant is only what? Is only NO2. And then see, we have the graph over here. Okay, we have the red graph over here. So the question is, what is the rate law for the reaction? Okay, so you see, we see the different type of graphs over here that show the concentration, like how the concentration CnO2 change over time. Okay, how the concentration NO2 change over time. Okay, to understand this one, we need to know the rate law. The rate law is K and O2. And then we don't know like this option N. Okay. Our goal is to find the exponent N. Okay. Our goal is find N value. Okay. So is it 0, 1, or 2? How we know that? Just by looking at each graph. Okay, looking at each graph and what it tell us. Okay, so now let's look at for the first one. See, this is time. This shows that the concentration is decreasing, right? Decreasing, but not straight line, not like over like this way. Okay, which is telling us this is not zero order, not zero or order reaction because not straight line. Okay, not straight line. Okay, so now let's take a look at this one, ln NO2 and then time. Okay, if the reaction, so okay, so for the first graph, you see the that just showed the amount. Okay, drop a curve down, which tell us that it's not zero order. Why? If zero order, it will be straight line going down. Okay, straight line going down. For example, this is NO2. For example, this is 4, 3, and then 2, and then if this one is straight line like this way, so it will be something like this, right? So this is the criteria of zero or order. Okay, the second graph, the this one also curve line too. If the first order, the graph will be straight line. So this is also not first order. Just remember, this one is NO2, this one is ln NO2, and then this one is 1NO2. And then the third graph, this is the straight line going up. Okay, whenever the graph of 1 over concentration is straight line, that means the reaction is second or order. Second or order. Okay, I just wanted to let you know, guys, that the first order criteria is speed is should be constant. And then a versus time should be straight line, because the rate is k. Okay, and then for the second, this is the zero order, and this first order. Okay, speed will be depends on the amount. Okay, so if and speed depends on amount, so if the NO2 is double, it will be double. Okay, so depends amount. Okay, ln A versus time, straight line. Okay, rate law is K and O2. Okay, and the second one, okay, same. Okay, same. First, and the speed is, I mean, faster than the first one. However, 1 per A versus time, it will be straight line. And then the rate is K is NO2 square. Okay, so if we have question like, I don't remember the concept of grab. Okay, what we can do, what we can do. Okay, if we don't remember that one. All right, so let's say we pretend we have some numbers over here. Let's say we have time 0, 1, 2, and then the concentration of NO2 initially is 1, this one is 0.5, and then this one 0.25. Okay, so now try for zero order. Okay, try for zero order. Okay, if zero order, rate is K. Okay, rate is K. Okay, so if time is zero, the concentration of NO2, it will be 1. If time is 1, it will be 0.5. And then if 2, it should be not 0.25, it should be, it should be 0. Okay, it should be 0. Now let's take a look at if we have like first order. If we looking at the first order. Okay, if we have like first order. So time, if the first order will be 0, 1, 2, okay, and then NO2, the time, and then for the Ln, NO2, it will be 0, okay, minus 0.693, and then minus 1386, okay. So this is first order. Hmm. So if we are looking at the graph, is this match, okay, is this match, okay, is this match, okay, if we are looking at this one, if this match, no, this one is not straight, okay. For example, this one is 1, and then if we have 2 over here, this is not 0.5. See, it's too long, it's too long, okay. Okay, so tell us not the zero order. How about the order Ln? See, for example, this is 0, okay. Is this 0 point, and then for 1, for example, over here 1, is this like 0.6? Probably. However, and then if we are looking at more over here, so is this the time, is this 0.13? No. Okay, it should, it's kind of like more. Okay, so from here, this is time, this is time 2, this is time 3. Okay, now let's take a look at if we have like 3, like the second order. If the second order, it will be 1 per NO2, it will be what? It will be 1, 2, and 4. See, looking at this one is 0, is coming from 1, and then if we have 2, it will be, so for example, like this one, okay, this is 1, right, and then it will be 2 over here, and then if we over here, it will be 4. Okay, so by looking at by like showing, to pretend we have kind of like number, we know which one that correct. So what's the answer? The question is, what's the answer? So the rate, it should be K, okay, and sorry, uh T is the NO2 square, okay, NO2 square. So the answer will be D. Right. And then now, move on to another question. What changes when a catalyst is added to reaction? Describe this energy diagram. Okay, now let's take a look at. So what changes when a catalyst is added to the reaction described by this energy diagram? So the thing that will change is the energy between, okay, the first one is the big hill, okay? This called is activation energy. Activation energy. This one is overall energy. And then the last one is energy between start and finish, or how much energy the reaction gives or takes. Okay. Now the question is what change if we add? So if we are adding, okay, if we are adding catalyst, it will lowers the activation energy. That means arrow 1 gets smaller. With this one it will be smaller. That means 2 and 3 stay the same. Okay, 2 and 3 stay the same. So if we adding, yeah, just activation energy goes down. Okay, is that number, what's the number it is? Okay, this is not overall. I think this one, after I'm checking, this one also activation energy. If the reverse reaction, this is if forward forward reaction. This is one is delta H for reaction. So the answer will be 1 and 2. Oh, okay. So you see, this is from here to here. Okay, this is the forward reaction, and then if we want to reverse reaction, is coming from here to here. Okay, so 1 and 2, the activation energy. Right. Okay. Now, which statement regarding chemical reaction is true according the collision theory? According collision theory. Okay, all molecular collision result in chemical reaction. Okay. So what okay, to deal with this question, we need to know what is the collision theory. Collision theory, okay? You need to imagine molecules are like balls bouncing around in space. Okay, for a reaction to happen, the thing must be true when they crash into each other. So they have to like hit hard enough, and then the other one is hit at a right angle. If either of those doesn't happen, there is no reaction. Okay, so now let's take a look at for the first one. All molecule collision result in chemical reaction. No, sounds nice, but it's not true, because if there is not enough energy, no reaction. Okay, no reaction. Okay, and then catalysts make individual collision more effective, increasing reaction rate. Okay, and then it looks good, right? This is actually pretty good because we know that catalyst itself, like, it help us was that it help us to decreasing the activation energy. And then you know that catalysts help particle line up better or better orientation, and then give them a shortcut by lowering energy hill to climb. Okay, so even molecules are already crashing, a catalyst make the crash more likely to work. Okay, so keep B for now. And then how about C? Okay, how about the C? Okay, proper orientation of molecule is required for collision to result in chemical reaction. Okay, this core part is collision theory. If two molecules hit a wrong direction, the piece doesn't fit, so no reaction. Okay, and then this one also looks like good. However, let me okay. So I don't know why there are two good option. Proper orientation of molecule is required for collision to result chemical reaction. Increasing the potential of reaction, decreasing the kinetic. No. So it's between B and C. Choice B is incorrect. Okay. Catalysts make individual collision more effective, increasing reaction rate. Yes, more effective, yes. Increasing reaction rate. Not not make it more effective, no. Yeah, the increasing reaction rate, yes. This is more effective? No. It just like provide the alternative way. Okay, the alternative way. Okay, to react, they will the catalyst will give us the alternative way. Okay, so the question is only collision theory, so it will be C. Okay, it will be C. Like I mentioned, they have to hit hard enough. Okay, just for like recap tip. Okay, recap, the collision theory said like reacting particle must collide. Okay, collide with enough energy and right orientation. Right orientation. That's all for the collision theory. Okay, the activation energy for particular reaction is blah blah blah. By what factor will rate constant increase when the temperature is increased from 50 to 60? What factor will the rate constant increase? Okay, now we can use the Arrhenius equation over here. Okay, the concept is testing here is about Arrhenius equation, which is we can use the K2 K1 E exponential EA R 1 T 1 minus 1 T2. Okay, so this is the equation. However, if we don't remember the equation, what we can do, okay, what we can do, okay, so we can do reasoning without math, okay, without math. Okay, temperature goes from 50 to 60, and then activation energy is 83.1. Okay, now think that's 10 degrees Celsius increase over here. The activation is pretty high, okay? Which means the reaction is too sensitive, okay, with temperature. Small temperature rise can have a big impact of reaction rate, okay? I'll mention again. Raising the temperature increase the reaction rate because molecules move faster and collide more energetically, right? So if we just have 10-degree difference, okay, we just have 10-degree increasing temperature, like increased temperature, and then the activation is this one, right? So what will happen? Okay, what factor will rate constant increase when the temperature is increased? Okay, now think that the rate should increase, maybe even double. Okay, maybe even double if we increase. Okay, now eliminate the option. For we start from option D. Okay, we start from option D. Hmm, that's not make any sense, bro. So the question is, what factor will rate the constant increase when the temperature increase from 50 to 60? Okay, remember that the increase is 10 degrees Celsius. The activation energy is pretty high, which means it's so sensitive with temperature. Okay, and small temperature will have big impact for the rate. Okay, so the option D, like we know this one is like a very very big drop. Okay, makes sense. No makes sense for increased temperature. And again, numbers of option C. This says rate constant decrease. That's opposite what we expect. Okay, we want to increase the rate constant. The K should be red because we increase the temperature. Okay, so if we have like one for if we have like one for K, right? This one is constant. This one is not. This one is not. This one. Okay, not decreasing should be this one. So for example, K2 and K1 is 1. Okay, if we increase, it will be more than 1. If we have like 1, it should be no change over here. There is no change. Why is dropping? This one is drop, and then this one is same, so the answer will be A. So if we don't remember the equation, if temperature goes up, okay, the activation energy is 0. Okay, it's not 0, sorry. The temperature goes up, activation energy is not 0, rate constant goes up. Okay? So if you are stuck to remember this one, just hotter, faster. Usually a lot of faster. Okay, the rate constant will be faster. Why this one is same, not 0, not 1. Okay? This is if we don't remember the equation. If we remember the equation, is pretty easy. K2 K1 E EA is what? Activation energy. Okay, activation energy in joule per mole, so it will be like this. Okay, and then uh R is 8.314. Okay, and then this one is should be 33315, 32315. So K2 by K1, if we using if we want to find out the correct answer, so we are getting ended up like E 0.939, which is around 2.56. Okay, if we remember the equation, if we don't remember, just remember the concept that it increased 50 to 60. So K will should be goes up. Okay, rate constant should be goes up, not go down. If we have K1 for in the original one, okay, there is no change, right? If we want, okay. So how what's happening if we increase from 50 to 60? It will decreasing, nope, nope, and then if will be same, nope, should be A. If we don't remember the equation, okay, just remember this one. Okay, now let's move on for another equation before. So still two left question for study question. So sometimes, not sometimes, oftentimes the study question is pretty much harder rather than in the real equation, because it tests us like the whole parts of these materials. Okay, Okay, now let's take a look at this one. Consider this reaction. A proposed mechanism for the reaction is slow and fast. What is the rate law for this mechanism? Okay, now let's break down one by one. So we have two step of mechanism. The first one is slow, the other one is fast. What's the correct law for this mechanism? Okay, so what we need to know here is in kinetic, the rate law is coming from the slowest step. Okay, slowest step. So we only care about the slow step. Okay, we only care about the slow step. Why? Because the slow step control is like I mean the it's like the bottleneck. Okay, bottleneck, that slow step control the entire flow. Okay, so it's like have a big portion in the reaction itself. From slow step, we know that the rate, it will be NO2 and then F2, right? Okay, so it's matched perfectly with the option C. Okay, so why the first? Okay, now eliminate one by one. And this one is equilibrium. Okay, this one is equilibrium, not rate. And then this one is incorrect. NO2 only one. Okay, and then F is kind of like, was that is intermediate, not the reactant. All right, sounds good. So just remember, only use the slow step, and then write law from the reactant in that step. Okay, don't include intermediate and products. All right, that's good. So the answer will be what? Will be C. Okay, now let's take a look at the last question for this session. We can continue after that. Okay, so consider the equilibrium. This one, the forward reaction is proceeding at a certain rate at some temperature and pressure. When the pressure increase, what might we expect for the forward reaction? Remember, if we increasing the pressure, okay, if we increasing the pressure, we will have much more collision. Okay, we will have much more collision. Okay, a greater rate reaction and greater yield. It will give us like greater yield. Let's see. If you stress a system at equilibrium, it will shift to relieve that stress. Okay, when we increase pressure, the system will toward the side fewer mole of gas. So let's count gas molecule. Okay, we can use the Le Chatelier principle. Okay, so if you increase the pressure, okay, increase the pressure, it will the system will toward fewer moles. So C, this is 2, this is 3. So which one that fewer? So the product, okay? The product. So increasing pressure favors the right side. which is more SO3 form. Okay, that's equilibrium. Okay, and then how about the reaction? This is about equilibrium concept. Okay, and then so remember, if we increasing the pressure, the the system will be towards to the fewer moles of gas. Okay, all right, if the pressure, we increasing the pressure, which is in the 2SO3, and then how about the rate reaction? We know that if we increasing the pressure, this is equilibrium. Okay, now increasing pressure, we will have like more collision, and then faster reaction rate. So it will be A for the final answer. Okay, so yield will be increasing for the product. Okay, and then remember, just if pressure up, shift to fewer gas mole in the equilibrium system, and then more collision. If we increase the pressure, it will increase the collision, which is increasing the reaction rate. So the answer will be A. All right. So we will continue for the next discussion in the second, I mean, for the next video. So still, I mean, we can continue after